So in the last video about stationary points, I mentioned something called the second derivative, but I didn't really explain what it was. In this video, we're going to kind of clarify what the second derivative is and how it's applicable in this unit or in this branch of differential calculus. So the second derivative is essentially the derivative of the derivative. So you start off with a function. Let's say it's y equals x squared plus 4x plus 2. The first derivative of this function would be dy over dx, which would give us 2x plus 4. And then the second derivative, which is written as d squared y over dx squared, which would be just 2, because it's differentiating 2x plus 4, which is our first derivative, to get our next derivative. I guess theoretically you could get a third derivative, which would be 0, because just differentiating 2 would become 0. But it's not really necessary to do. It's quite futile. So we can just stick with the second derivative. So in this case, x squared plus 4x plus 2 would give a second derivative of 2. Okay, so to help us understand how second derivatives relate to this part of the unit, I've just pulled up one of the questions we tackled in the last video, where we determined any stationary points on the curve x cubed minus 3x squared plus 3x plus 4 and their nature. So finding the stationary points themselves and their coordinates, we do not use the second derivative at all. They have no part in it. So we have to go through the normal first derivative process where we find the first derivative and we equate to 0, and then we find the x values, and then we find the corresponding y value. But determining the nature, which is determining the fact that it's an inflection point, that can use second derivatives to help us. So the way we did it in the last video is we constructed a table like this, where we had the point over here, 1, 5, and we checked points on either side of it. So we checked the x value, which is 0, and the x value, which is 2, and we saw the y values corresponding. And we saw that increasing from 0 to 1 increased the y value, and increasing from 1 to 2 also increased the y value. So when it comes to drawing this kind of situation out, we had a positive gradient and a positive gradient. So that showed that it was an inflection point. But there's a much simpler way of doing so and checking this. First thing we have to do is find the second derivative of this function. So we'd find d squared y over dx squared. So we saw that the first derivative was 3x squared minus 6x plus 3. So the second derivative would be 6x minus 6. And 6x minus 6, we can just substitute our value of x in the stationary point in and see what it gives us. So in this case, we had the coordinate 1, 5. So we just substitute the x value into the second derivative, which gives us 6 times 1 minus 6, which is just 0. Now, there are a couple of things we need to know about how to interpret the value we're given. So we're given a value of 0. The way we can tell the nature is if d squared y over dx squared is greater than 0, then it's a minimum. If d squared y over dx squared is less than 0, we're given a maximum. And if d squared y over dx squared is equal to 0, it's an inflection. So, based on these set of rules, we have gotten an inflection point, because the second derivative, when substituting the value of the coordinate in, gives us 0, which satisfies this rule over here. Since the second derivative is fairly easy to grasp, I'm not actually going to show how it works with another example, but I'm going to show some of the reasons why you should take it with caution and also use alternative methods just to prove that it's correct. Because let's look at one example where the second derivative happens to not work. Let's take the function y is equal to x to the power of 4. And I'm going to put up the graph of this function on the screen right now. And as you can see, it has a distinctive minimum point at the point 0, 0. So looking at this function, we can tell that it's minimum, right? However, when we take the second derivative, so let's first take this first derivative, dy over dx, which gives us 4x cubed, and then d squared y over dx squared gives us 12x squared. And since our minimum point is at 0, 0, let's try substituting 0 in there. Well, 12 times 0 squared is just 12 times 0, which is just 0. So 12, 0 squared is equal to 0, which suggests that we have an inflection point. But we don't, because when we look at the graph, it's clearly a minimum point. So, therefore, we can tell that the second derivative test does have a few exceptions. So while the test does have a few exceptions, it is pretty much still 98% accurate, and it does work with 98% of the graphs. So I think it's just with ones that have like perfect lines of symmetry, like x to the power of 4, x to the power of 6, x to the power of 8, and they have even powers, except for x squared. Then they tend to give inaccurate representations. But on the whole, the second derivative test is pretty accurate. Like, it would work, for example, with really complicated things like logarithms and ln and e to the power of x. But with just simple equations like x to the power of 4, which are so symmetrical, it may have some errors. So that's why it's always good to use that kind of table formula or sign diagram to check your work afterwards, just to ensure that the second derivative test has worked. And if it hasn't, then you should trust the sign diagram more than the second derivative test. And so to cap it off this video, let's just look at the steps again to using the second derivative test. Number 1, find the second derivative. Then number 2, plug in the x coordinate of your identified stationary point. So all this is assuming that you've already found the stationary point, and you can find out how exactly you do that in the last video. And then 3, you would check your resultant value against the rules to determine the nature of the stationary point. Sorry, I'm writing really quickly, so it's pretty illegible, my handwriting, but essentially what this means is that if it's greater than 0, then you have a minimum. If it's equal to 0, you have an inflection point, and if it's less than 0, you have a maximum. So I would memorize these rules. They're quite simple to remember. They're just 3 different rules. But it will help you greatly when using the second derivative test to find the nature of points, and it saves you a lot of time. So all this will help you identify if you have a maximum, minimum, or inflection point. And so that's pretty much it for the video. There are not really any worksheets to add for this part because it's pretty easy. Like, you can just use it with random problems you come across with stationary points. You don't really need to have separate problems to do this practice this kind of concept on. So yeah, I'm not going to attach worksheets to this video. Thanks so much for watching, and see you in the next one.